Okay, so today we're going to talk about BLAKE3. And basically, I'm moving most of my SHA-256 and 512 logic to BLAKE3. And the reasons are because BLAKE3 is super fast, is highly parallel, is very flexible, such as we can ask the length in bytes of the hash we want to get, and then is as strong as secure as a SHA-2 family. So first, we're going to do a very simple case where we're going to hash some string, and then I'm going to show what I like to use sometime in production with base 58 and why. Then we'll look at the keyed version of a hash, such as very similar to what we get with hashMac and 256 or 512. So those are very good for web token. Then we'll see how we're going to hash some small and big files, and I'm using that quite a bit for the hashing technique, because again, it's very fast and very efficient, and so it compares pretty well against the SHA-256 and 512. And finally, we'll show how to do the custom length for the hash. Okay, enough talking, let's start coding. So first, make sure to use BLAKE3, the version 1. We go to our simple. We're going to do cargo watch extension, C01, simple. We have that, and the way that it works is that let's say that we have let input, and we're going to say hello world. We're going to do the one with update. So you can create the whole hash with a one new, but I like to do the update. I'm going to explain why. So you do a let mute hasher, and you do the hasher from BLAKE3, and we do a new. That will create a new hasher over there. And then to add the data, we do a hasher update input as bytes. And the reason why I like this way, rather to have there's another new here where we can pass the data, is because if you want to add more, like for example, you have some salt or whatever, you can add more this way. It's a little bit more idiomatic this way. And then to finalize the hash, we're going to do a let hash, hasher, finalize. And that will finalize our hash. Press save, nothing will get printed, that's normal. And then we're going to do some prints. First, we're going to print the hash x, and so that we just do a 2x on this one. So that is this type from Blake, and then we can have a 2 hexadecimal like that. And then we are just going to print the length to make sure that we understand, because this actually by default is like SHA-256 or 512. It's always 32 bytes. Press save, and now we have the hexadecimal of the hash, and we have the 32 bytes. So far, so good. Now, we're going to add some timer to make sure that we know how long it takes. So we're going to use a standard time, and then we add this one, press save, and now we have basically a 0.05 millisecond, which is pretty good. And that will become more useful later when we're going to do the B files. Now, one thing that I'm not a big fan of, obviously, is the hexaserialization of the hash. This is kind of a pretty long. So we have a couple of ways. We can do a base 64, or actually one thing that I like a lot sometimes is base 58. So for that, we're going to go to our cargo to ML. We're going to add the base 58. So that is a new crate in a way. So it's BS 58. And then we have the base 64. So like this, we can compare. So we're going to press save on this guy. And then we'll go back there and we're going to add those two lines, which is one to encode the hash, the one that we got over there, we get the bytes and we do the toString. And then the other one, we're going to base 64 and actually base 64 U, which is URL notepad. Yeah, this one. So we press save. We're going to import that. And then there's going to be the other guy over there. And now just below the hex, press save. And now we can see that that is a big hex kind of things. The base 64 is just one character less. And here in this case, there's no weirdo guys, but there could be some special characters, which is URL safe. So that's the good news. But I actually like quite a bit often base 58 because there's no special characters and it's also human friendly where it removes some of the ambiguous characters. So usually I use that if I use a BLAKE3 to hash a big file and I use this hash in another file name. So this is a technique I'm using and I will use that guy. So this is pretty good. But again, you can use a hex, you can use base 64U, anything that works for you is actually a good one. Okay, so now we're done with that simple guy. Okay, so now let's do our second example. So we're going to take this one and we're going to rename it like that. That will be our second one. And we are going to do a cargo watch example. So that is basically my best practice when I learn new crates. Okay, so we're back there. So on this example, we're going to remove this. We don't need to carry that over everywhere. We're going to keep the rest. And the way it works here for the keyed is when you do a simple hash like this one, it's great for hashing big files, small values, and so on. But it's not as brute force or whatever as a hashmark 256, for example. And the way to do that in Blake is to use a new, so they have a thing here which is new keyed, like that one. And that takes a 32 bytes key. So there's multiple strategies to generate a key. One that I like is to use UUID v4. So that has a good entropy and everything, and usually is a safe bet. So we're going to use that, go back to our code, and now we're going to generate the keys. And so one thing that we can do is something like that. We have the key, and we're going to import UUID. I'm going to close that. Now, the trick of that is that this key, if we put it there as bytes, is not going to work because it expects an array of 32 and it got only 16. So there's a couple of ways we can have that. One is to derive that key of 16 bytes to 32 by using actually hashmark. So we'll do something like that, where we take our base key, we do a string, and then we use BLAKE3 to hash it as a byte, and that will give us a 32 array by the spec, and then we can use that. I'm not saying that that is good, but that is one way, and now it works. Yeah, so we have these kind of things. We took one key, which is 16 bytes, and then we use BLAKE3 to create a hash, and by default the hash is 32 bytes, and so we can use that to do this. Now, that doesn't have the maximum entropy, obviously, because this 32 bytes is based on the 16 and is always the same. It kind of works, but it's not optimal. So what we're going to do is we're going to take this one. So I like to have different examples. So like this, when I come back to it in a few months or whatever, I can see the different stages and just cherry pick what I want. So that will be the new name. We make sure to restart our CWE with a new guy. So now, first what we're going to do is rather to generate only one UUID, we're going to generate two UUIDs. And then we're going to create our key, which needs to be of the key length here, which is a 32 bytes. And then we're going to copy the first part and the second part, like that. That will give us a new key, which is obviously a U8 of 32. We press save, and everything should work exactly the same. So in this case, we have kind of maximum entropy, because we get two UUIDs, and then we just concatenate those, and then we use those as a key. Now, the way that often happen in production coding, you don't have a key like that in your program because you have it somewhere in your secret. For example, in Kubernetes, you will have them in Kubernetes secret, you manage by KMS or whatever. And so what I usually do is I take the key, I have a tool that will generate that, and then we'll generate this key and then do a base 64 out of it. And then when I put it in Kubernetes, I need to base 64 again when it's put in a secret. So that's sometimes a little bit confusing because it has to be double base 64, such as you get the last base 64. But in this example, it works very nicely. We have our key over there, which has a 32 bytes, and then we do the new key, and then we get the things like that. And then here, if you do a web token, you might add the user ID or user UUID or the expiration date and so on, and then kind of your hash, and that would be the signature part of your token. So that works very well. So that is pretty cool. And in a way, the keyed technique over there is good for anything which is signature or anything which is web token and these kind of things. So that is great. Now, what also Blake is awesome at, it's doing a hash of small or very big files. And this is very efficient for it. And so that is what we're going to do in our next example. And then this one, we're going to actually start it from scratch. So C04, we're going to call it, and files. And I'm going to put the repo here in the link, such as you can go and get what you need. So for this one, we're going to start from scratch. And what we're going to do is we're going to have implementing our function, which is going to be our fn hash file. and it will take a path. And usually what I like to do is something like that. That is quite flexible as ref path, and that will return a result of, for the demo, will be the use64, which is going to be the size of the file, the string, which is the hash, and then the duration. So that will be the duration from standard time. So that is a way that we're going to do it to kind of display the time and so on, but obviously this could be done another signature. But the point here is that it will return that. That is what it should return. And I'm using the best practice here of my error because we're using result multiple places. I do a type alias, and I like to use again my boxed in. So this is what I have. So I'm going to put the to-do over there, and if I press save, it should almost compile. I'm going to have path over there, close that, and I'm going to do a CWE C04 files. And now we're in business. Okay, so now, first thing here, we're going to get the path to make sure that we have the reference of path. Then we're going to open the file. Then we get the metadata. So this is just for the file size. We don't really need it, but in this example, we want to have it so that we get a sense of the file size. And then here is the important part. So we are getting the reader, the buff reader. So what we don't want is we don't want to read the whole file in memory and then creating the hash with the bytes of the file, because we don't know the size of the file. So if it's a small file, it will be okay. If it's a big one, then it will be suboptimum. So what we want is to get the reader, and then we create the hasher. Then we're going to start our timing. And in fact, to be fair with the other ones, the timing should be above. And then what we do is we do a IO copy, and the reader, which is going to read the file, will write to the writer, to the write trait, which is this guy. So a hasher is going to implement the write. For now, we're going to put the to-do over there, and we're going to fix the import. So that is a buff reader from standard. That is the instant. That is our hasher for BLAKE3. That is our file, and that is IO. So good. And that works because the hasher implement the write trait. So if we come and click there, we're going to see that that takes a read trait and a write trait. And typically that, the buffer size will be 8 kilobytes, which is what we want anyway. And then later, we're going to see how we can write our own buffer if we wanted to have full control. Okay, so now what we're going to do is we're going to finalize the hasher like we did before, exactly the same thing. We're going to end the timing, and then we're going to convert the hash to hexadecimal, like we did again before. And then we're going to return the file size, the hash, and the duration. So if we print save, obviously we don't print it because we didn't wire this up yet. So first, what we want is we're going to iterate through our two files, which is going to be this file, the C3, that will be the small file in a way, and then this one, which is this guy, which is the big files, which is about 200 megabytes. So that is to understand the spectrum. So we're going to do a for file in files. We want to make sure that we're going to skip if the file doesn't exist, such as if you git clone this repo, you won't have the big file, obviously, and so it won't fail. And then the only thing we do is we're processing the file. We're going to call hash files. If there's an error, we're going to print it. Otherwise, we print the size, the hash, and how long it took, which is actually the duration. We're going to align everything nicely, press save, and then the small files takes 0.5, and then the other one takes about 2 to 3 seconds. So that is pretty cool. So we're going to press save again to make sure we get about the same numbers, and we get about the same numbers. And note that the key is always fixed. Yeah, by default is a 32 bytes. So in this example, what we did is we use a default IO copy to copy the whole file with the default buffer. Obviously, if we wanted, what we could do, I'm going to create another file for that, custom buff. We could go there, and then we could replace that with our own buffer size and so on. So we'll say buffer size 4 kilobytes, for example. And then we have our buffer. We're going to read. We make sure that we get how many bytes we read, because at the end, it will probably be less than 4 kilobytes. And then we update the hasher with what we have read. Yeah, so we need to make sure that we don't forget that. Otherwise, it will be the old values, which it will get some weird numbers. And then we finalize, and then that's it. So if we press save, it should compile. Probably need to import the read over there. So that is the old guy, which 2.7, so 7 seconds. Now if we stop stop that, and then we do a CWE, this guy, and it should be about the same numbers if it's not exactly the same. Yeah, about the same. So it doesn't really change that much. The point here is that you control your buffer size, which if you really want to. Otherwise, usually, for me, I'm going to use the default one. So that is what I'm doing, but we have the flexibility of using whatever we want. So now the question is, how does that compare to SHA-256? So first, we're going to go to the cargo. We're going to add this one, because now we're going to do the SHA-256. And we're going to go pretty fast on this one. We're going to create a C06 files SHA.rs. I have everything copied here. I'm cheating a little bit. And we're going to use right now 256. So basically the same kind of things, almost same logic and so on, except that now we are using SHA-256. Yeah, so it's the same kind of things. So I'm going to stop it, CWE, C06 SHA, and then press enter. This one is about the same time, and this is about 3 seconds. Oh, actually, I'm sorry. So that was a 512, which is a little bit over 3 seconds. If we use SHA-256, press save, we'll see that it's a little bit longer on this guy, and it's much longer on this one. It's about 6 seconds, sometimes 6 to 7 seconds. So the nice thing here is from SHA-256, BLAKE3 kind of saved quite a bit. In SHA-512, in some CPU, is much faster, but it's still kind of slower than BLAKE3. So for me, BLAKE3 is my go-to. And then the last one here we're going to do, just to complete the example, is going to be the custom length. So usually it's a custom hash length. So usually it's 32 bytes back. But when we do something like that, we can have our custom length. So in this case, we're going to set it to 64. We can set it to anything we want, obviously. And then we create the hasher exactly the same way. Then we do the hasher update. Whatever data we have, we could have the files as well. It doesn't really matter. The length of the data doesn't matter on the length of the hash. And then we create our buffer, and that is where we're saying finalize XOF, and then we do a fill. That will fill the buffer with its length with the data. And then we encode it here. So we use XEncode because now this guy is just a reader, so it's not anymore a hash of Blake. So this is why we probably need over there to have something like that. And again, in production, I will probably not have these sections, but this will give us a hint. And I press save on that. That should compile. And then I do a CWE C07 XOF. And then that's it. So that is basically the hash length. It's 64. I don't print everything here. In this case, we're doing only the first 16 bytes. And that takes, again, it's very fast. But now we have full control on the length. So that is pretty cool. Anyway, I'm a big fan of BLAKE3 and obviously the BLAKE3 implementation in Rust, which is very high quality. Hope you like this video. Big thanks to Crab Nebula for their sponsorship. Until next one, happy coding.